Hello and welcome back. Today, so we just did this problem. See, this one's also on the video for the other one. So there's a different video for problem 7. But today we're going to look at problem 8. So quest 7, problem 8. And we're asked, what is the angle theta? So that is up here at this situation. We have our angle theta here. Okay, and we're asked to find that angle. So let's go on down here and we'll draw our free body diagram for this situation. So we've got our object, which is at an incline. We're told that it's frictionless. So that is a good thing. We know that is true. And we have our weight force, which points down. That's going to be Fg. And we have our normal force, which points this direction like that. So those are our forces. From here, I'm going to break the weight into components. So we have this. That's our parallel component. This is going to be our perpendicular component down here. Just a quick reminder that this up here, up and down the slope, is our parallel direction. And into and out of the slope, like that, is our perpendicular direction. Just a reminder. Okay? So, what do we know already? We know that the weight is equal to mg. And we know that this perpendicular component of the weight is mg times the cosine of theta. And we know that this parallel component is equal to mg times the sine of theta. Right? So we know all of that. Okay, we've got that set. We also know there isn't any friction. So this is our free body diagram. What else do we know? Let's see. I forgot the tension. That's what I forgot. We also have our tension force that goes this way. I knew I was missing something. So we have our weight, our tension, and our normal force. Those are the three forces acting on this object. So what else do we know from up here? We know that since this block is accelerating downwards at 6.1 meters per second, and they're connected, just like a normal Atwood machine, any distance that this one goes down, this one's also going to go down the ramp. So we know that this block that's up on the ramp must be accelerating down the ramp also at 6.1 meters per second squared. So I'm just going to make a little note of that. I'll do it in here. We know that it's accelerating down the ramp, all right? And we're asked to find the angle theta. So we've drawn our free body diagram. That's a check. Now let's move on to our normal next step, which is going to be Newton's second law. So I'll do this in black. This isn't as exciting, but I'll do it in black. So actually, I'll do it in orange because this is a parallel. We're going to be working in the parallel dimension. So you know that the sum of the forces that is parallel to the ramp is equal to the mass of the object times the acceleration of the object. We know both of these things, which is good. So let's look at this. Since the acceleration is pointing down the ramp, we're going to call that our positive direction. Okay? So that means that our net force, or the sum of all of our forces in the parallel direction, is going to be T plus mg sine theta equals ma. Since they both point down the ramp, they're both positive. That's how we get that. Now we're trying to solve for this angle theta, right? So we need to get this theta alone. So first, let's just do some algebra. Let's move the tension over to the other side. So I get mg sine theta equals the mass times the acceleration minus the tension. Okay? Now we're getting closer down to our theta. Let's divide both sides by mg. So I get that the sine of theta equals ma minus t over mg. Okay, let's do that. Now we're almost there. We're almost at theta. Now all we got to do, since we have sine of theta, we just need to use our inverse trig functions. So we get that the theta, the angle theta, equals the inverse sine of this big old nasty fraction. ma minus t, the mass of the object times its acceleration, minus the tension in the string, over the mass of the object times the acceleration due to gravity. And that is our angle theta. And thankfully, because we calculated the tension in the first one and got that it was 5.35 newtons, we know everything here and we can solve for our angle theta. So let me substitute in my numbers. I get theta equals the inverse sine of, let me scroll up. What's the mass of this box? 4.1 kilograms. We have 4.1 kilograms times the acceleration of the box, 6.1 meters per second squared, minus our tension, which we figured out was 5.35 newtons, minus 5.35 newtons, all over the mass, which is 4.1. Whoa, you moved on me. 4.1 kilograms times the acceleration due to gravity, which we know is 9.8 meters per second squared. So we have that big expression, and that is just a number. So let's go ahead and plug it into our calculator. We get that theta equals the inverse sine of 4.1 times 6.1 minus 5.35 over 4.1 times 9.8. Now with things like this, make sure that you are being super careful about your order of operations. When you're plugging things into a calculator like this, that's really kind of crazy. It's always better to overuse parentheses than to underuse parentheses. That way you just make sure that you are getting exactly what you're wanting to get and the computer inside your calculator doesn't get confused. So I get that theta equals 29.3 degrees. And that is, in fact, my answer. So there we have it. That's how you find the angle theta for this behemoth of a problem. Hopefully that is helpful. I know it's a lot of algebra, but it's all algebra that you can do because you're a physics rock star. You got this. Okay, good luck, y'all. And remember, use your numbers and not my numbers. The algebra is the same. The numbers are different. Sweet. Later, y'all.